Good morning to everyone. So welcome to a 5-day YAN course on non-invasive fault diagnosis of propulsion motors using electric vehicles. So today is the third day. So in the yesterday discussion, with the Professor T. Lamparthi garu, so he has discussed about detecting and diagnosing air gap eccentricity faults using machine learning algorithms. So in the morning session, Professor Lamparthi has discussed about and explained the algorithms like KNN algorithm and the principal component analysis algorithms. So further, the participants, we have had a lab visit in the electrical engineering department, the research labs, some various labs were visited. And further in the afternoon session, so whatever the discussion happened in the morning with respect to the algorithms, so we have tried to put an attempt to implement these algorithms in MATLAB software. So that's what yesterday's session. Today's session, so we have a session on building an experimental setup with different eccentricity faults of various reactors, and also implementing artificial neural network to classify the eccentricity fault types. And further, sir will discuss about these algorithms. So hope you will be getting good knowledge about conceptuals in the beginning for this session. So over to you, sir. Professor Lamparthi, sir.
Thank you, sir, for the review and introduction. Good morning, everyone. I hope you all had some relaxing evening and all had breakfast this morning. So we will get started with the session. This morning we will be discussing on two different topics. So one of them is on experimental setup, how to create a test bench in your labs if you want to work on air gap eccentric fault related research. Okay. So that is the first part of the presentation. It should be reasonably brief, it wouldn't take a lot of time. In fact, we will start with a simple activity where you will be going through a couple of literature publications focusing on experimental test bench, and then I will share how I, in my lab, have utilized whatever is available in literature to create an experimental test bench. Okay? This will also give you an idea of what equipment you already have, what you might have to explore in terms of security, and those kind of questions we can discuss. The second part of this morning session is going to be focused on machine learning algorithm. It's strange that we just started with a fundamental or very elementary algorithm like KNN yesterday, and then the next day we are planning to deep dive into artificial neural network. I will try to introduce it in a manner that you all can get a grasp of basic terminologies, and then I will show you how tools like MATLAB can be used to apply artificial neural network algorithm for our purpose, which is fault diagnosis. So So that's the thing. So we will just get started by doing an activity. I see that the projector is yet to be showing up on screen. So maybe we will. It is not going to affect us because we are going to start with an activity. I have shared a couple of research articles in the group. So what I expect you to do is maybe take 5 to 10 minutes max, not more than that. In both articles there is a section on experimental setup. I want you to just read that section only. Okay? Open up the 2 articles one by one, go through the experimental setup sections. Maybe in 5 to 10 minutes we will reconvene and I will start discussing about how I have implemented these ideas. Thank you. For those of you that have just come, the idea is we start with a simple activity of reading through a couple of literature articles focusing on the experimental set.
just focus on the experimental setup section. You don't have to be there. It's just paper. Electromechanical energy conversion. It's more mechanical than electrical. Another couple of minutes, maybe last 2 minutes. Let us maybe start discussing.
If the activity is done, you have read the articles. The main thing that I want you to understand is when you buy a motor from any manufacturer, it's designed to have no eccentricity. It is manufactured, assembled to have no eccentricity. Everything is designed to work in a proper way, right? So when we want to introduce a fault like this, we have to kind of rip apart the motor in some sense and then introduce mechanisms to okay. So maybe I should speak louder. Okay, thank you. So we have to make modifications to the enclosure, to the mechanical setup, to introduce such a fault. Okay. More or less, there are only two approaches that I have seen in literature to introduce air gap eccentricity faults. The one that I am going to say is what I have in my lab currently, and this is reasonably easy to make compared to some of the setups that I shared with the article. The compromise is, with the setup that I am going to present, you can only achieve certain fixed or discrete values of eccentric severities. Okay, you cannot achieve like continuous variation of eccentric severity. So you can only decide whether you want 15% eccentricity or 20%, 25% like that. And the magnitude of fault will also be reasonably small. It cannot, like you cannot achieve 50% typically, because it is going to be extremely high. So let us consider I got a motor under study. This is a synchronous machine. So this is how we got it when we bought it from the manufacturer. This is a 3-phase 2 kilowatt salient pole 4-pole machine designed to work with DC field, DC excitation. So it's a traditional synchronous machine. So this is the original enclosure. So what we did was we took it to a machine shop and we ripped apart the original enclosure. So we took apart the original enclosure and we replaced it with a modified enclosure as shown here. So these are end plates. So I hope you can see the end plates now. This is one, this is another. And then there are 4 bars which houses the stator in place. So this was done in a proper shop. So we cannot do it in a lab using like people who are not trained to assemble things. You cannot do it. You need proper measurements, proper training to do this. And once the stator is properly placed, the rotor can be housed inside this. So this is just the enclosure change and the end bell change. So end bell is now modified. And this is basically the idea that has been mentioned in research article 1, where they have replaced the end bell with cutout to place eccentric bushings. So eccentric bushings were then created for proper dimensions and with very low tolerance. And this bushing is what will help you level shift your shaft. So the bearing will go inside this groove, but what will happen is it's eccentrically displaced. That means on one side it is having higher height than the other. So the entire bearing will be placed off center the original in a position. So if you consider the original point as C1, then when you place the bearing inside this bushing now, and when you connect the shaft, the center will no longer be at C1, it will be displaced by a fixed distance, which these are polymer bushings. It's hard rubber, I would say. Yeah, to place the bearing. I'll show you in the next slide. Okay, so this is an outer bushing. So the outer rays of the bearing will be touching this inner surface. Okay, and this you can decide how much displacement you need in any direction. So it can be in one direction only. So it can be either this way or this way or this way or this way, it doesn't matter. But that is the direction of offset. And you can decide how much severity of eccentricity you need. So if you think that the original machine had an air gap of 10 mm, and if you want to offset by 2 mm, then this bushing should result in that offset. So when you place the bearing and load the load the shaft, it should be moved up or moved to one side by that 2 mm offset. Okay, so that is the idea. So whenever you have such a bushing, the most important thing is you need to know where, because it's circular, you need to actually have a mark somewhere to identify where the offset is. Okay, because otherwise when you mechanically mount it, you may not mount it in the proper positioning. On two sides you have to make them symmetrical, right? Otherwise you will result in a tilt. You don't want the tilt to happen. Incidentally, these bushings have six, like you see four, like basically 1, 2, 3, more like a delta points or a triangular vertices, 3 holes, and then there are also 4 side holes, right? So some of these holes are to affix the bushing onto the end plate, so you can thread a screw through these holes, and some of them are just to unmount the bushing from the end plate. So what happens is, even if you unscrew, you may not have the bushing come out easily, so you will have to use the anti-clockwise rotation of another screw to take it out. Okay, so these holes are primarily to remove the bushing from the end plate, some of them, and some of them are just for fixing the screws, or basically fixing the bushing on the end plate. Okay, the dimensions will be based on the bearing you want to use. So if you know what bearing motor is supposed to have, then based on that you can decide the dimensions, and the air gap will determine the offset, or the eccentricity severity will determine the offset. The bushing on the right side is a bushing that will help us achieve a wobbling motion of the shaft. So what we are trying to do is, when we put the shaft through this hole, this is not circular, it's elliptically cut. So you will see that the motion will be wobbling. So you will get dynamic eccentricity. And by the margin or the distance of, in the way it's eccentrically cut, will determine the dynamic eccentricity severity. Okay? So how you will do is, you will take the original motor, you will replace this enclosure, you will change the end bells. You will also have to replace the bearing, because the original bearing might not be able to fit in these eccentric sleeves and bushings, right? So what you may have to do is, you have to look for a new bearing. So we looked at and found a bearing that would suit our requirements for the machine under consideration. And this is a sealed bearing, so you don't have to lubricate it. So that's a good thing. In the lab environment, it's better to have such bearings. If you have another type of bearing, you may have to lubricate it frequently, which is not convenient. So what we will end up getting is an arrangement like this. So you will put outer bushing, the bearing, and then the inner bushing. And this entire arrangement will be going on to the end plate on both sides, and the shaft will go through the hole that is visible. In fact, if I go back a couple of slides, you will see a keyway for the shaft to go and lock. Okay, so this is also important. Otherwise, you will see slipping between the shaft and the bushing. So you should have a keyway to make sure that the shaft can be locked at this point, and there is no slippage between the bushing and the shaft. Now, if you want healthy condition, your bushing on the outside, bushing on the inside, they both will have 0 offset. So that is one set of bushings that will have 0 offset, which will result in healthy operation. So the air gap will be uniform around the machine. If you have only static, if you want only static eccentricity fault, then the bushing on the inside will have 0 offset, but the bushing on the outside will have some offset. If you want only dynamic eccentricity fault, it will be the other way around. Okay? And when you want to have a combination, both the bushings will be offsetted bushings or eccentric bushings. Okay? So this is how we can achieve different combinations. Now the drawback of this mechanism is, first, if you want to change operating condition, so you want to study healthy motor, then you want to study static eccentric motor or dynamic eccentric motor, and vice versa, then you have to stop the motor, remove the end plates on both sides, remove the shaft or rotor basically, and then replace the bushings. Okay? So that is it's a laborious process, and every time you remove and assemble, you probably are going to introduce some kind of additional fault. Like your assembling has to be precise, and if you are not trained to do that, you may end up resulting in unwanted situations. Okay, so that is something to keep in mind. So the major drawback is you have to remove the bushings every time you want to change from one operating condition to another operating condition, or one fault condition to another fault condition. The second drawback is, as I said earlier, because these are discrete offsets, you can only achieve certain severities of faults. You cannot achieve any severity of your liking. Okay, there are only 3 or 4 severities you may have. After cut multiple bushings and keep, and you can replace one at a time, but usually there will be 3 or 4 combinations you will prefer and you will use them. So you may get 10%, 15%, 20% like that in both static and like the outer and the inner bushing, and then you will combine them to get different types of mixed eccentric faults. Okay? So these are the 2 major drawbacks of this arrangement. Having said that, this is probably the easiest to fabricate and implement in any setup. Okay? So if you have a machine shop in your institution, they can easily get this done for you. It is not too difficult. The only thing you need to be careful is the tolerance when they cut these bushings, because that is going to impact your severity of eccentricity considerably. Okay? So you need to be cutting these bushings to a very strict tolerance, because we are in millimeter range, so our tolerances should be in micrometers. Okay? So that is something. So the overall thing is, you take the original machine, you modify, you put this, and then you remount, and then you get a different condition that you want to work with. Okay? So this is the base preparation of the machine. Once that is done, you have to now connect this machine, basically create a circuit. So what I have done is, I have used a 3-phase salient pole synchronous machine. I am loading it electrically using a DC machine. You can load it in different ways. If you have a brake drum, you can use it. If you have a dynamometer, you can use it. And this 3-phase synchronous machine it can be inverter driven or fed from lines like utility supply. What I have done is, I have used utility supply, but this machine is rated for, if I'm not wrong, 208 volts line to line, and the supply I had was a 480 volts supply. So I had to use a step down transformer. So this is not needed if your supplies match. You may just use a variac and you can get it done. Okay? And then I measured the stator of this machine is Y connected with a neutral point not brought out. Okay? So the stator of this machine was Y connected with a neutral point not brought out. And therefore, I know that in a system like that, the currents and voltages, the sum of instantaneous values of currents and voltages should be equal to 0. And therefore, I just measured the 2 line-to-line voltages and 2 line currents. Okay? I did not measure anything else. But ideally speaking, you should be measuring 3 line currents and 3 line-to-line voltages in the setup. So one thing you will notice is, I have used a differential voltage probe, because that's how you can measure between 2 lines. And I have used a Hall effect current sensor, which is a clamp-on current probe. And these probes will have their own attenuation factors. So the differential probe was set to measure 500 volts and translate it into 1 volt. So it's a setting of 500 to 1. The current probes were set to 10:1 basically. So 10 amperes of current would be converted into 1 volt. That's the idea. And all this data have to be sampled and acquired for data processing. So you need a data acquisition system, and that data acquisition system should be capable of sampling the signals of interest at a rate which is fast enough to capture the highest frequency component of your interest in the signal. Okay? So this is very important to keep in mind. Even though the line frequency is only 50 or 60 hertz, you know that harmonics might be there, and if you want to capture fifth harmonic. So 300 hertz is the frequency, right, for a 60 hertz system, or 250 hertz. It's a 50 hertz system. So your sampling has to be done keeping in mind the highest frequency component of your interest, and then you have to sample it in such a way that you wouldn't lose that information. So if you sample it at a higher rate, you will be able to do that. So a data acquisition system in which you can sample at a high enough rate so that you can capture some of the lower order harmonics of your current and voltages would be quite helpful. Especially if you recollect the MMF permeance analysis, we found out that there is kind of a sideband frequencies. So if you have 50 hertz, you get 75 hertz, 25 hertz. So the 75 hertz is greater than 50 hertz. So that should be used as your frequency of interest if you are trying to capture. Okay, so you may have to capture based on that kind of higher frequencies. Okay. As you know, based on yesterday's information, I have sampled at 3600 hertz or 3600 hertz, which is sufficiently large enough. So even if I have fifth order, which is 300 hertz, 3600 is like 10 times that, right? So I will get more than 10 points of 300 hertz waveform. So I should be able to capture up to fifth order quite easily. Okay? So that is the basic idea of sampling, and then that will get stored in some memory. So I have used a PC to save that. Okay? So this is the setup. What is not shown in this setup is, because this is a DC excited rotor winding, you need a DC supply to connect to the salient pole rotor, and you will have to start as an induction motor and then synchronize it later on by turning on the DC power supply, just like how you would do an experiment. In case of EV motors, most of the modern passenger electric cars and the low light electric vehicle motors are permanent magnet based. So and then they will be driven from an inverter. So the test bench will be slightly different. You will have a supply from the utility that is feeding the motor. You will have a variac, and after the variac you will have a three-phase inverter. And typically for a permanent magnet motor, you will need to sense the position of the rotor and create a closed loop to drive the motor. Okay, so it's a little one step more. So you need to know how to do that inverter driving of a PMSM before you can get into the actual data collection process. Okay, so these are a few things. So just some photographs from the setup. May not look pretty, give you idea. So I am showing some line currents. You can also measure line-to-line voltages and feeding it into a data acquisition box, which I probably had. And these are like technologies have changed a lot over the last several years. So you probably already have sophisticated equipment at your disposal. So yesterday I was chatting with a couple of you, and there is oscilloscopes nowadays have storage capability, and most of them are 8-bit. So you have to check whether 8-bit is sufficient or not. But any low-cost microcontroller might be able to get you data acquisition at a reasonable bit, like 12-bit is quite common, right? So you should be able to do that. ADC count is quite easy. So you can use that to acquire data. So you may not have to invest in expensive equipment from data acquisition is concerned. You might already have it. You might buy low-cost components as well. Yeah, it depends on many factors. The data acquisition system can be quite pricey. If you really want higher resolution, like 16-bit, and higher sampling capability. Simultaneous sampling of 1 mega samples per second might be quite pricey. Yeah, these are reasonably pricey equipment. In fact, this is an older equipment. We are no longer using it. We are using a more recent version from National Instruments. The reason why we prefer National Instruments is It has a LabVIEW software which helps you visualize the data as you acquire it. If you are in NIT or IITs, you will have access to all these tools. But if you are in another institution, you may or may not have access to these tools. You don't need necessarily such expensive equipment is what I'm trying to say. Exactly. So most of the modern oscilloscopes already have digital storage capability. The only thing you may have to check is the resolution of those oscilloscopes ADC system. If they are 8-bit resolution, it might work out, it might not work out. So you have to try it out, okay? Depending upon the voltage signals that you are working with and the current signals you are working with. Okay? Yeah, so this is the major thing. So this is what I used. So what are the things we can change in this setup? We can change sampling rate. We can change the number of signals that are sampled simultaneously. If you have a data acquisition system that can capture up to 8 channels, then you can capture field current also. You can capture 3 line currents. You can capture 3 line-to-line voltages. So that is 6 signals plus 1, 7. And if you have vibration sensors, you can add them, mount them onto the machine, and vibration signals can also be acquired. Nowadays, there is thermal imaging that is also being captured. There is a temperature sensors output that is also being captured. So if you have a good enough data acquisition system, which is sometimes quite useful to invest in, you can capture a lot of signals simultaneously. Now, the simultaneous capturing of signals is quite useful from machine learning perspective, at least initially. Later on, you can capture them one at a time and see their impact. But if you can capture all the signals simultaneously, then it helps in your machine learning implementation. Okay? The problem with such a setup is because it's open enclosure, it's quite dangerous. So you cannot have anyone who has no training to go and work on such a setup. You may end up losing an arm, sometimes even worse, when people go and work without having adequate training and safety. Okay, so whenever you, and these machines are rotating at high speeds, right? So you have to be really careful. And because they are open windings, like carrying high currents, you need to be really careful as well. Okay. Accidental short circuit should be avoided. So in a setup like this, protection is critical. The diagram does not show any protection, but it is not how it will be. You will have fast acting circuit breakers along the lines, loss of excitation. In a lab setting, because it's it's okay. It's okay to do that, but it's better to have loss of excitation detection and appropriate protection for that as well. And then mechanical protection, wearing safety glasses just to protect your eyes. These are some mandatory procedural parts. Okay. So this is just because of my lab power supplies were not matching. So I had to do this arrangement. Otherwise, if you had a power supply that matches with the machine's rating, then you just need a variac to control the startup transients. And if you are doing an inverter, you can easily implement startup transient control in inverter itself. But most of us would prefer to use a variac because it gives you extra layer of protection. So the transformer here? Yeah, that gives isolation for sure, but the intention was not isolation in my case. It was primarily just voltage matching, level matching. Okay. So this is how I did it, and the plan now is to go forward. So one thing I want to caution you is all this setup bushings, like this arrangement will work out well if you do not have a permanent magnet in your rotor. So if you are planning to use a modern EV motor, which is a permanent magnet based, and most of these permanent magnets are rare earth magnets, they're extremely powerful. What does that mean? So you cannot pull it out or push it in as per your liking. So this approach of having eccentric bushings which can be replaced is not going to work out for a modern permanent magnet based motors. So if you have invested in a permanent magnet based motor, then I have shared the second research article in which you would have seen the enclosure is modified such a way that you don't have to remove the bushings. There will be screws that you can push in or pull out, and that will adjust the level of shift offset that will be applied onto the shaft or to the bearing. Okay, so that's the idea. So you have to be very careful in realizing the fact that this arrangement will not work for your permanent magnet based motors. So the arrangement that's going to work is what I showed in the other research article, or what you saw in the other research article. Okay. So that is something for you to keep in mind, because our intention is mostly on propulsion motors, right, used in electric vehicles. This type of synchronous motors are also being used in electric vehicles. Okay. For example, some European car manufacturers, they use DC field excited synchronous motors just because they want to avoid rare earth magnets. Induction motors are also used in electric vehicles, especially off-road electric vehicles, high power electric vehicles. So all these are still propulsion motors only, but if you are looking at a permanent magnet based motor, then definitely you need to look at a different type of test setup to introduce eccentric fault. So is this okay? So this is the setup. So whenever I say I collected data, a setup like this is what I used, and this is how I collected data. So there can be many sources of noise in this setup, or even error when we collect data. So for example, the probe setting, the attenuation factors might be noted incorrectly. Or the Hall effect sensors, the clamp-on type sensors. In some settings, they are battery operated. So if the battery is low or drained out, data acquisition might not be proper. So we might not even notice that the battery is drained. There might be an indicator, but you might not have noticed it, and you would have collected data and you will see that there is zero line or just a straight line. So what I'm trying to say is you need to really inspect the raw data as you collect, and then only you can conclude whether this is good enough or not. So you still need this expert knowledge to check whether you have a sinusoidal looking wave, three-phase waves that are equally spaced. One of the common mistakes I made while I collected data was the current probes, they are direction sensitive. If you put it in one orientation, you will get one. So I placed the two current probes in opposite orientations. So when I acquired the signal, the line currents were not displaced by 120 electrical degrees. So when I visualized it, I realized that something is not correct. So then I checked. Of course, once I know what problem I did, I didn't have to repeat the experiment. I just inverted my signal, one of the signals in software. So, but what I'm trying to say is there are many sources of error in data acquisition that you might end up doing. Okay. So, are there any questions at this point? Okay, so if not, let's move ahead to the next topic. So as I switch to the next topic, this is not experimental setup, this is more an introduction to ANN. So this is what I will be doing in the next couple of hours, I would say. So between now and 12:30, we will be talking more on ANN. As I said, yesterday we started with a very basic algorithm like K nearest neighbor, and today we are deep diving into artificial neural network. How many of you have some experience with ANN? Like, has anyone worked with ANN before? A few of you, okay. So you know some basic terminologies, hopefully. So this session I'm planning to introduce you to the very basics of ANN. Like we will not go deeper in the mathematical component. we may try to do some simple exercises towards the later time, but my primary intention is to do this. I want you all to be aware of certain terminologies by the end of this presentation. Why this is important is because in most of the application-oriented research, like what we are doing, ANN is a tool that we will be using, right? And we need to understand what these terminologies mean and how we can utilize them for our research. Okay? And there are lots of tools available in the market. So MATLAB has an ANN toolbox. You have PyTorch. You have many tools, right? So you can use them, but you need to understand what those mean, and then you can effectively use them. I will do a very basic explanation of the working of ANN. Okay, yeah, you should take it with a pinch of salt, in the sense that it may not be precise explanation, but it is an explanation that will get you started. Okay, and you have to read more to understand this after that. And then finally, the more important aspect from my perspective is how I have implemented this to diagnose eccentric fault from a healthy condition. So that's the main intention. So maybe in the first 45 minutes or so, we will focus on the basics. In the next part, we will look into some implementational aspects. Okay. Okay. So before I do that, I will want you to take a moment. For those of you that attended yesterday's session, day before, I hope all of you have access to a piece of paper and pen. Everybody has? Okay. So I'll give you 1 minute. So 1 minute is to think, and then I will give you another 1 minute. So think of any point that you did not understand either yesterday or day before from those presentations. And then what I want you to do is write that one point that you did not understand, or you are confused, that's not clear to you in your mind, on a piece of paper. Okay? And then that is what you are going to do now. So I'm going to give you time until 10:17. Okay? So think of one point that you did not understand, not more than one point that you did not understand, the topmost unclear point, and then you are going to write it down on a piece of paper. So I hope all of you have at least captured one point, or could think of something that you did not understand. So please write it down on a piece of paper. Don't hesitate. Your handwriting will be much better than mine. You have seen mine, right? So don't hesitate to write down. Write on a fresh piece of paper, because you are going to do something with that paper now. So after you have written on a fresh piece of paper, you are going to crumple, okay, and then you are going to hit a target that I am going to show you. Let's see how good you are at it. So I have a chair on this corner, and there is a tray. I think it's a tray that's covered with some purple colored cloth. So you have to land your paper on that target from wherever you are located. You cannot come forward, okay? So that's the exercise you are doing. So crumple the paper. Some are lucky they are closer, but that's how life is. Yeah, if you are done, you can start throwing your questions to the chair. Don't hesitate, please go ahead. Hard luck. Close. Okay, let's see if anybody can land it on the tray properly. Please be quick. Oh, almost. Okay. Now I also will know who had breakfast this morning. Okay, by the time you throw, I will find out. You should not throw at me, you should throw at the chair. Okay. Maybe I should give a prize for those that gets it right in one attempt. Anybody else wants to do it, or are we done? I don't see few people yet to throw. Okay. Last 10 seconds. We are running out of time. This was supposed to be a quick exercise. You can stand up and you can. Close. Okay. Anybody else still to do? Okay. So this is, I do not know if you have ever seen this exercise before in your class. Have you done it or have you seen it? No? We call this as popcorn. So what we end up with is popcorn. Okay. We will usually have a bin for popcorn, and students have to create, like fill the popcorn bin during the class. Anyways, so that's fine. That's not important. Okay. So we will get started with this second topic. I think we have had a nice activity. So the main intention of this presentation is going to help you understand the basic terminologies associated with artificial neural network. So first, what is artificial neural network? So artificial neural network is a field that got inspired from a biological neuron and the way biological neurons work. I am not an expert. I don't have any knowledge of how biological neurons work, but my elementary knowledge says something like this. So if you have a biological neuron, as shown on the image here on the slide, there are multiple nodes, like multiple points, through which sensory information can be collected. So these are the input points. So these are the finer, they are called as dendrites. These are the input points. And all this input goes into one area of the neuron, neurocell. And then there are many aspects to it. And what you will see is there are nodes, the terminal buttons, which may have an output based on the information received, or it may not have any output at all. And that is the beauty of a biological neuron. So the output or the neuron may fire an output or may not fire an output depending upon a threshold. Okay? So the output depends not only on the input but also on a threshold. Consequently, we have a non-linear behavior. So you must understand what is non-linearity. So a step function is a non-linear function because up to some point you have 0 and then suddenly it jumps, right? So there is a non-linearity in there. So this is more like a step function where you see a non-linearity. So the neuron output may get activated, may not get activated, depending upon the threshold that is to be hit or not. Okay? So there are a set of inputs, there is an aggregation mechanism, and then there is a threshold. Based on the threshold value, the output may appear or not appear. So this is how biological neuron, I should not say this is how it works, but this is the inspiration behind artificial neuron. Okay? So with this idea in mind, if we can abstract this idea into an artificial neuron, the way artificial neuron can be thought of is, let us say we have an artificial neuron, it will receive multiple inputs. So these are all inputs, let's say x1, x2, x3, x4, like that. The first thing it will do is it will aggregate. Okay? So aggregation means summation. But will all inputs be equally weighted? Probably not. So some information might be weighted more, some information might be weighted less. So we will introduce a weight for each of the inputs. So this is a weighted sum of all the inputs, and there may be some bias inherently or added to this system. So there may be some bias to this system. Oops, bias. So the output here will be the weighted sum of all the inputs plus a bias. So W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 plus a bias, let's say B. That will be the output. Now this output, if it hits the threshold or not hit the threshold, will determine the output of the neurocell. So after this, we need to have what we call as a non-linear activation function. So the non-linearity of the neurocell is captured mathematically using, like, say, a step wave or any non-linear function that you can think of. A diode rectifier, for example, is a non-linear function, right? So anything negative is cut out, only positive comes through. So that's a rectification unit is a non-linear function. And then what you get is the output. Okay? Usually you will not see two circles shown, rather a single artificial neuron will be indicated using one circle where there is an aggregation of weighted sum plus bias, and also an activation of nonlinear activation function, usually indicated by a letter. I am using G, you can use any activation function symbol. Okay? So this entirety is captured in single circle, and this is how an artificial neuron is represented. Okay? Is this clear? So the inspiration is biological neuron. It's a gross abstraction. It's like it's not that simple how a biological neuron actually works. It's grossly simplified abstraction. Even this grossly simplified abstraction is doing wonders from a computational perspective. Okay? Then imagine the power of our neurocells. So what is really interesting is, like some of you might be aware, that until this point, until this section, everything is just linear operation. So if you don't have any nonlinear activation function in your system, and if you directly take this as output, you can get a linear regression model. A model, linear model basically. A regression may or may not be to your liking, but linear model, let's say. The moment you add nonlinear activation function, you are going out of linear mode and you can get different types of models. The most fundamental single neuron based model, which is widely used around the world for binary classification, is called as logistic regression. And logistic regression uses the single neuron structure. So it will take multiple inputs. It will have aggregated weighted sum plus bias, and it will have a nonlinear activation function. And this nonlinear activation function in a logarithmic regression model would typically be called as a sigmoid function. So this is maximum of 1, minimum of 0. What does that mean? If the input going into the nonlinear function is a negative value, minus 5, minus 4, let's say, something like that, then the output of the nonlinear function will be very close to 0. On the other hand, when the input to the nonlinear function is a large positive value, the output will be very close to 1. And when the input is close to 0, the output will be somewhere between 0 and 1. So this function is called as a sigmoid function. Mathematically represented as 1 over 1 plus e to the power minus x, where x is the input going into the nonlinear component of the activation neurocell. Okay. So if you just want to do a binary classification like what we have, we can do a logarithmic regression using a single neuron. It's not a neural network, it's just a single neuron, and we will still get good results because we are introducing a nonlinear function. Okay. In this presentation, we are not going to look at such a structure, rather we are going to look at a neural network. So what is a neural network? A neural network comprises of multiple neurons. Let us say there are 3 neurons. To the left of the 3 neurons, I have inputs. I am indicating the input, let us say using an orange circle. Orange might not be visible, so let us use a different color. Purple, let's say purple circle. So I have 5 inputs, x1, x2, x3, x4, x5. I have 3 neurons, and let us say I have 2 outputs. Oops. A neural network is something like this. So you will have one layer of input, one layer of outputs, and something in between will have a layer comprising of neurons, multiple neurons. And this layer is usually called as hidden layer. Okay. So the hidden layer is the layer in which we have neurons, artificial neurons. So if I have to relate to the slide that I showed previously, to the one I have here, the way things will work is something like this. So let us say, these are the inputs. So each input will go to each of the neurons. there will be weighted sum 1 associated with x1 and associated with cell 1, right? So you may have a double subscript or a subscript and a superscript depending upon how you want to do it. So 1 1 w1 2 w1 3 like that. And then the second input will also have weights associated with each neuron. So this will be w21 w22 w23. All these weights are scalar, merely numbers, okay, nothing else. Likewise, you will have all the 5 input points connected to all the 3 neurons in hidden layer. The neuron will do a weighted sum of all the inputs. Then there will be a nonlinear activation function within the neurocell, and the output of that will go to all the output entities in the output layer. So let us just use the same color. So you will have output going like this. Okay. What is interesting is you will see an output. There will be a value here. So we can consider these as weights as well. And these are also neurons. So these are output layer neurons. Neurons in the output layer. So there will be a summation here and a nonlinear function even in the output layer. Okay. So the input layer, we have inputs. They can be treated as neurons or they can be just treated as inputs. Hidden layer, we have neurons. The output layer also has neurons. And these neurons will receive input from the hidden layer. And there will be a weighted sum plus a nonlinear activation function. And finally, the output of the output layer is what we call as a prediction of the output variable. Okay? Is this clear? So we have one layer which is hidden, one output layer which is exposed, but both are neurons. So the output layer will also do okay. You will have y1, y2 like that. Okay. So this is a simple structure. What we will end up getting is a more sophisticated structure. So usually you will see there will be multiple hidden layers. 1, 2, 3 in one layer, 1, 2, 3 in another layer, or 4 in another layer, and then you will have output. And then you will have maybe 5 or 6 inputs. So you can have multiple layers of neurons arranged. And whenever you have layer greater than 1, the hidden layers greater than 1, we call this as deep network. When layer number or hidden layer number is greater than 1. Hidden layer. So this is the invisible part of our brain, right? So like it's like so it's where all the intelligence happens or decision making happens. Or in other sense, you can consider this entire thing as a black box. What you give, what you get is what you have access to. So nothing in between is actually accessible in that sense. Okay? So when you are talking about deep learning, what you are trying to do is you are trying to increase the number of hidden layers. more than one. And if you have more than one, you can have 2, 3, 4 like that. The more layers you add, the more complex your system becomes. Okay? So this is the general structure of an artificial neural network. Okay, so I hope I have introduced you an artificial neuron and a basic network. So some key terminologies. So the first is with respect to the input layer. Let's say, so this is x1, x2, x3, x m minus 1, xm, let's say. So if there are m inputs, first of all, what are these inputs? So we have learnt about inputs to artificial or a machine learning model yesterday, right? What are the inputs from our yesterday's discussion? Features. So this is the feature vector, essentially. So if you have kurtosis, RMS, these are the features, right? In our application, the number of features we have is limited. But but in typical cases, the number of features can be several thousands, several tens of thousands. So what we will do is we will not feed all the inputs all at once into the neural network. Rather, we will be feeding only a portion of the input features at a time to the neural network. And that kind of dividing the input layer into smaller sets is called as, each one that is divided is called as a batch. So you can actually, if you have lot of features, you can divide them into smaller batches. Usually the batches are uniformly distributed or uniformly divided, and therefore you will have, if there are n batches, like m divided by n batch will give the number of elements in each batch. Okay. So the second layer is the hidden layer. For most applications like ours, one hidden layer is enough. Worst case, you may need 2 hidden layers, but 1 hidden layer is more than enough for most of the applications that we will be doing, at least in this workshop. Okay? In hidden layer, you have size of layers. So it can be 1, 2, 3, 4, 5 up to, let's say, L. L be the size of layers. Okay? So there are L neurons in a particular hidden layer. So you can have 10 neurons, you can have 2 neurons, you can have 20 neurons. So you can have more neurons within that one layer. You can also have more number of layers. Rather than having one layer only, you can have 2, 3, 4, 5 like that. Okay? So layer size is the number of neurons within a hidden layer. Number of layers is how many hidden layers you have. Okay? So now let us look at a system, an artificial neural network, which has an input layer with 3 inputs and a hidden layer with 2 neurons or 2 entities. How many weights are there in this system? So each input, if it is connected to every neuron, there are 2 per input. So this is 2, 2, 2. So 3 input entities, 2 entities in the hidden layer will result in 3 cross 2 weights. Okay. If I have another layer, then this will have 2 neurons, so this is 2. So this will be 2 cross 2. If I have one output layer, there will be 2 cross 1. So the total number of weights in the system is 3 cross 2 plus 2 cross 2 plus 2 cross 1. So that many weights are there. So what we are trying to do is, of course, what I have ignored is the biases. So each of this, when we add, aggregate sum, there may be a bias associated with this element. There may be a bias for this element, bias like that, for each of the neurons, right? So there may be plus number of biases. Number of biases is usually equal to number of neurons in the hidden layers. So what we are trying to do using an artificial neural network is we are trying to fit a curve for a given set of data. So it's basically a curve fitting kind of a problem. Again, these are all very simplistic terminologies, so don't like this is a good starting point, okay, in the way you can think like that. So we are trying to fit a curve for the given training data set, and that curve fitting will have this many number of unknowns. These are the weights and biases that need to be determined to do a proper fit. Okay? So 6 plus 4, 10 plus 2, 12 plus 4. 16 unknowns to do a curve fitting of mapping 3 inputs to 1 output. So the reason why I am saying that is, if you increase the number of neurons, if you increase the number of layers, or if there are more inputs, more outputs, then the number of weights will increase considerably. And what we are trying to do using an ANN model is to determine these weights and biases. So the more weights and biases you need to solve for, the longer is your training time for your model. One terminology I probably forgot to tell you, maybe ahead I should have told you ahead, is the network that I showed you, where each entity is connected to every entity. I'll put it this way. So each neuron in a hidden layer is connected to all the inputs, right? So basically, if each entity is connected to all inputs of the preceding layer, so if this is the neuron and this is extended, right? So neuron 2 will also be connected to all. Each entity in any layer is connected to all entities of the preceding layer. What we end up getting is called as a fully connected network. Usually abbreviated as FC. Until I learnt about neural networks, for me FC was football club. Okay? So now it's a fully connected neural network. So we will be discussing only about fully connected networks. So in any fully connected network, the number of weights in the network depends upon the number of input elements, number of neurons in a hidden layer, number of hidden layers, and number of output elements. So the more complex your system is, the more number of weights you need to train. Okay? And of course, the number of biases will also increase. Compared to the order of weights, the number of biases will typically be lower. So that's something for you to keep in mind. Okay? Okay. So this is just about the first thing. The next thing is, let us look at again a system. Let's even simplify it further. Two inputs, x1, x2. So these are features. Kurtosis, RMS, like that. So you have learned how to generate them from a raw data set yesterday, right? And let us say we have a neuron. Just I will draw it bigger. It has two components, right? One is the aggregation plus bias, and then there is a nonlinear function. This nonlinear function is called as activation function. Because in biological neuron, a neuron is activated or not activated. And that is why we call that as an activation function. Activation functions that are typically used in neural networks are, so activation functions or nonlinear functions. So first one is sigmoid function, and this is what is used in many logarithmic regression problem. We typically use sigmoid function. This is widely used in artificial neural networks. Another type of function is a tan hyperbolic function. A tan hyperbolic function, if I plot it, it will be going from +1 to -1. So it will have exactly the shape of a sigmoid curve, but it will be centered about 0. A sigmoid is like level shifted above 0. It goes between 0 and 1, whereas a tan hyperbolic is centered around 0. So it's slightly advantageous in some applications. So this is tan hyperbolic. So tan hyperbolic, you know the equation, e power x plus e power x minus e power minus x divided by e power x plus e power minus x, right? Something like that. I don't remember now, but you can refer to the resource. The third popular activation function is rectified linear unit, usually abbreviated as ReLU. What is a rectified linear unit? A rectifier. Imagine a single diode rectifier. What will it do? If the input is negative, it will block. The output will be 0. The current cannot go through it. If the input is positive, output will just pass through as it is, right? So the rectified linear unit's output waveform will look like this. It will be 0 for all negative values of input, and it will just be output is nothing but a linear. The input itself will go as output on if it is a non-zero value, positive non-zero value. Okay, so this is the wave shape of rectified linear units function. So this is a very popular activation function. There is also a leaky rectified linear unit function. You may or may not use it, but we will not get into those things. ReLU is good. We will stick to that. Okay. A leaky means we will not have 0 here. Any diode will have leakage current, right? So it is just to indicate that there will be a non-zero value which is slightly above 0, considering leakage of a diode. Right? So it's a leaky rectified linear unit. Okay. The last one, which is very popular in output layers, is what we call as softmax function. Softmax activation function takes in an input and gives a probability of an output. So the higher the value of input, higher will be the output, but it will be a probability. A probability can be only below 0, right? So the output will be between 0 and 1. So the output of a softmax function will be between 0 and 1, and depending upon the input, If the value of input is very high, the output will be close to 1, otherwise it will be close to 0. So these are the popular activation functions. So typically you can have any of them in your hidden layer. You can choose one activation function for one hidden layer, another activation function for another layer, another activation function for output layer, like that. Okay? So that's good. The last one I will do before break. It is just a probability function, sir. So you basically will get an output which goes between 0 and 1. It can take any value between 0 and 1. Depending upon the input magnitude, it may be close to 0 or it may be close to 1. So it's just a probability. So there is no, yeah, it's like there is no mathematical representation, like pictorial representation will have. Okay. I don't think we call them membership functions. I'm not too sure. Maybe usually they are called as activation functions only. So sorry. It's a probability function. Oh, I don't know. We can check that. Okay. Yeah, I mean all these are mathematically captured. There are all equations behind every function, right? There is nothing. Yeah, you can choose any of the options. I'm just introducing you the terminologies now because in my application, I'm not going to deal with lots of these things. What I'm going to use a tool. I'm going to use my data set, and I have to select what are the functions I want to use for my application, right? So that's the key. And so typically a rectified linear unit is preferred whenever you want to avoid the problem of vanishing gradient. So that is the one major reason why rectified linear unit is preferred whenever we want to avoid vanishing gradient problem. Those technicalities we will discuss later. But I'm just giving you the terminologies now, if for those of you that are not familiar. Okay. The next thing is so in fuzzy, yeah, yeah, fuzzy membership functions usually are like yeah, they are very different in some sense. So yeah. Yeah, we usually have a triangular or a trapezoidal, so they're not completely nonlinear in this sense. I mean, they're also, they are not very popular. So the most popular activation functions are these functions. Okay? So they are typically, so the general idea is to capture the biological neurons behavior, right? So biological neuron behavior is like that of a step function. It goes from either activated or it gets activated. Like it's a discrete change kind of a thing. So the closest is sigmoid. It goes from 0 to 1. But then mathematically we have some drawbacks when we implement it, so we go for tan H or a rectified linear unit like that. Okay? So that's the idea. So the next terminology I want to introduce is like this. So we have an output layer and we get a prediction. And we will know whenever we are using a training set, typically for supervised classification, we will know what is the ground truth. So the ground truth is the actual output or actually known value is usually indicated as y. Y hat is the predicted output from the neural network. If the predicted output does not match the actual output, and there will be a variation, right? There is a difference, or it can be plus or minus. So the difference is usually called as a loss function, usually indicated by the letter J. So loss function is the, you can mathematically represent it in many ways, but in a very elementary basis, it's the difference between the predicted output versus the ground truth, or the difference between ground truth and the predicted output. And what I must inform you right away is, in ANN, we will always assign values to these outputs. We will not be looking at labels, like we are only looking at numbers. So ANN always takes in numbers and maps to numbers. Okay? So they are very good for regression kind of an modeling. But even for classification, we are looking at number input, number output. So that is why the loss function is always a number. Okay? So loss function is the difference between the ground truth and the predicted output. Okay? The loss function can be considered as a mean absolute error or mean squared of error, or it can be a more sophisticated function. For example, there is a function called as binary cross entropy function, which is typically used in logarithmic regression or any binary classification problem. You have different types of loss functions. So again, there are mathematical equations for all these functions, and the goal of ANN is to minimize this loss function, to make sure that the predicted output matches with the ground truth. So it's a minimization problem at the end of the day. So once we have estimated the loss function, we have to do this recurrently or recursively, or I should not use recursive, in an iterative manner to minimize the loss function to as low a value as possible. Okay? So see, these are some of the basic terminologies associated with ANN. So with this, we'll probably stop, we'll take a break. When we reconvene, we will go deeper and we will see how ANN actually works and what challenges you will have to overcome to implement it, and thankfully what tools you have at your disposal. Okay? Thank you. Again, and excellent. So where I left is the definition of a function called loss function, which is basically what your neural network predicts versus what is the actual truth about the output. Okay? And it can be mathematically in different forms. The simplest is just the difference, mean absolute error is one of the easiest loss functions you would encounter. Okay? Okay, so now that you all had some break, we will get started with a simple group activity. Okay? So what I want you to do is maybe work in pairs or teams of 3 if you're sitting beside 3 like each other. This is a very interesting activity. It's a fun activity. It's not about the answer, but what I want you to do is write how you are thinking. Okay? So the process that you are going to follow to answer a problem I'm going to throw at you has to be documented. So you cannot just chat, you cannot just think, you have to write it down. Okay? At the end of 10 minutes, we are going to discuss the steps. And that is the most important thing to understand how artificial neural networks work. Because at the end of the day, ANN is inspired out of the way we think, right? So if we can understand how we think, it's easier for us to understand the algorithm. Okay, so here is the problem. 2 persons go to a grocery store. One buys 3 kilograms of rice, 5 kilograms of wheat, 1 kilogram of sugar, 4 kilograms of lentil. and this person pays rupees 1345. Okay. The other person buys 80 kilogram of rice, 60 kilogram of wheat, 50 kilogram of sugar, 100 kilogram of lentils. Probably is another store owner, or is having a function at his place. This person pays rupees 22,368. The store has given some discount to the person that is buying in higher quantities. Very typical, right? Volume discount will be there. So now if I ask you to predict the per kilogram price of each of these items like rice, wheat, sugar and lentil, you are going to follow a method, right? So all I'm saying is predict the prices of these per kilogram price. What I want you to do in this activity is work in pairs or work in teams, but capture your thinking. What will you do first? What will you do next? Okay, so that is the activity. Is the objective clear? Any questions? So if you must predict the per kilogram price, how will you do it? Is my question to you. So I'm not interested in the answer, but I'm interested in the method. Okay? So you have 10 minutes, or maybe we'll start with 5 minutes. If needed, we can extend. Okay? So team up. If you are far apart, sit beside each other, discuss, and then document. First discuss, then document. Okay? It's important to understand this. Okay.
Yeah,
repeat myself, the objective is not to solve the problem, but come up with a method, what you will do. And there is no right or wrong method. Right? One approach is to go to the grocery store and ask. So that is not possible because we do not know which grocery store to ask.
Again, it's very one process to another.
So you come up with a method, mathematically, how do you approach such a problem? So write down steps. Step 1, this is what I will do. Step 2, I will check. Step 3, I will repeat. Something you will come up with a loop, an algorithm, basically. I am expecting English sentences. Okay? I am not expecting equations or anything like that. Just for your information, I am expecting plain language sentences. Like this is what I will do. First step, I will check condition.
Sir, from which part we how to find that? Okay, we will make some sentences until unless we know that the solution. So, how we need to proceed the solution we have to write this kind of thing.
So the question is, like two people are buying same items but of different quantities and they are being charged different prices. The problem thrown at you is what would be like if you want to guess the per kilogram price, right?
Rice or maybe whatever.
You just come up with a way to price. So what will you do initially? Let's say you assume a random check like that. Right? That's the idea.
So you are simplifying the problem. You solve, let's say you reduce to 2 equations, so not 4 prices.
So we need
What
prices.
is it? And then what is it?
So final objective is we need to find the
Price.
price. So let me take like the price of ICM should be
Let's see.
same. So
You predicted some value, right? That's fine. But after that, what do you do?
it is needed to compare.
Because you will assume. So you can check with that.
Again, same way.
So how will you do that? Will you still keep them same or will you different? So that is the idea, right? I think in general what I understand is working with engineers is very mathematical. You are trying to do everything mathematically that you have forgotten to keep things in plain language form. So what I was expecting was something slightly different from many of you what you have done.
So what I thought was, since we have been discussing about artificial neural network, what I thought was you would be you will say, okay, I will assume 4 numbers, one value for the price of each of these variables, right? So let me assume per kilogram price of rice be 100 rupees. How many of you actually go to a grocery store? Or even, oh really? You still do? You don't do online shopping? Oh, okay. Okay. So you should know the price of rice, wheat by heart. You don't even need to solve this. You can say, right? So you assume a value for each of these 4 unknowns. Don't take a variable. Assume a value. So there is a fine difference. Okay. What I have seen in all of you is you have been using X, Y, Z, and then you are looking for another alphabet. There are only 3 alphabets, X, Y, Z. Which other alphabet should I use? This is the problem you all have. But that is not what I'm intending. Use a number. Let price of rice per kilogram be 100 rupees. Price of wheat per kilogram be 80 rupees, something like that. Okay? So initially assume a value for the unknowns. Then what will you do? You have values, right? Kilograms, quantities. So with that price, multiply with kilogram. So let us say, let rice per kilogram be 100 rupees. Rice per kg 70. Okay. 70, 60. You are not eating basmati rice. That's what I understand. So then you are going for wheat per kg. 80. Wheat is more expensive here. Okay. And then sugar 40. And then lentil. Lentil is usually most expensive. So 100 rupees per kg, let's say. So now we have 3 kilogram rice. So 3 into 70 plus how many kilograms of wheat? 5 kg wheat. So plus 5 into 80 plus 1 into 40 plus 4 into 100. Okay? Do you have this? So you total this 1050. Then you will check a condition. Is volume discount applicable? So you will check if volume discount applicable for this buyer. Yes or no. So it's either 0 or 1. 1 means 5% off. Okay, let's say. So 0, no discount. So this value passes as it is. Okay. Is this, so this is the prediction. This is the final rupees that your algorithm has predicted. But what is the value the customer has paid? 1345. So this is y hat. Y is 1345. What is the error? 1345 minus 1050. So you can say that 295. But how is the direction? What is the direction of the error? So which the prediction is lower than the actual value, right? So prediction is lower than actual. Do you understand? So you are estimating the cost to be 1050, but the actual cost is 1345. So what will you do next? Increase the price of the items. Excellent. How will you increase it now? So let's say we add 2 rupees, 2 rupees, 2 rupees, 2 rupees. Constant increase. Is that what you will do, or you are going to increase it differently? Based on weight. Based on weight, you can increase the price. So each of you can have one way of changing the variable, right? So let us say we do it. Let us say in second iteration or second try, you revise the numbers. Okay? Instead of 70 per kg for rice, you make it 100. Okay. So you suddenly increased it to 100. Okay. That's a big jump. Okay. Now you switch to basmati rice. Okay. Fair enough. Okay. So try to do one more algorithm, like one more try. So let's say price of rice is 100. What about wheat? 79. You want to decrease it. Okay. Let it be 79. But why would you decrease it when you had an error which is positive? Okay. So 79, 100. 40 becomes 40 or 40 becomes what? 45. 100 becomes 150. Okay. Your rate of inflation is very worse. Okay. So now you do the math again. You please tell me what happens. Please, quick. We have invested in you by supplying tea and pakoda. Supposed to react quickly. So the first learning from this exercise is don't use such numbers like 79. Multiplication becomes difficult. Sorry? You got 1340. Wow. So you get 1340. Okay. Okay. This is not a very good way of formulating an problem, but I'm idea, right? What you are trying to do. So you will check with the actual value 1345. So the error has gone down. Okay. So you are seeing that the error has gone down. So you will again reiterate, right? But ideally, we want each of these weights to be as close to the right value as possible. But you never know what the exact price is. You are only making a prediction to get the output matching with the ground truth. Right? So the weights can be different and you may still get a similar number. Right? That is something you need to understand. So there is no, it's not a unique solution. Right? There might be multiple solutions because you had two equations, 4 unknowns. Right? That's what you started with. So this is ANN. Except we are missing some key pieces. Right? So what we have here is we had 1, 2, 3, 4 inputs. We can even consider them. So let us say there is an aggregation, right? Plus bias. And then there is a non-linearity. What is the non-linearity in this problem? So whatever weights you got here, you have not checked for the other condition. Right? So you have missed one condition. So when we did the iteration, we started with original weights, 70, 80, 40, 100. We got an error, but that is for one prediction. For the same values, if you substitute these numbers, these are the weights corresponding to the second neuron, right? You should get a second prediction as well, right? So if you do that, you may get a different. So here you have two neurons, one giving output y1 hat, one giving output y2 hat. Our goal is to ensure both the loss functions are 0, or the overall system is predicting both, for both scenarios 0. So what is the non-linearity? The non-linearity is the volume discount. So once you have aggregated, you check whether there is volume discount or not. If the volume is beyond 30 kilograms, then you apply discount. Something like that. So that is the non-linearity in this problem. So essentially you will have 4 inputs to this, 4 inputs to this. You will do an aggregation plus bias. So there are 2 biases, B1, B2. And then there is a non-linearity function, which is the volume discount. And you get y hat 1, y hat 2. And this you will compare with ground truth y1, ground truth y2. You will estimate a loss function j. This entire step is what we call as forward pass. So one forward pass means we take one set of input, complete input. If you are reducing it into batches, then all batches have to be completed. All inputs have to be passed through the neural network. It will go through all the hidden layers. It will go to the output layer, and output prediction is being made, and you are able to solve for the loss. And that complete step is called as one forward pass. Okay. So in this, we don't even have a neural network because this is input, this is output already. Ideally, we will have one more layer here, which is the hidden layer, and then the output. Okay. Okay. So the structure that I have drawn is not a neural network in that sense, because we are missing the hidden layer. We are having input and output layer only, but there should be a hidden layer as well. at least one hidden layer with a few neurons. Okay? And to solve such a problem, we probably will need one layer of multiple neurons, because it's an ill-defined problem, right? So you may have to do multiple looping back and forth to get this. Okay? So this forward pass, once we complete, you get a loss function. Now actually is where the problem starts, mathematically speaking. This is where network's algorithm actually kicks in. After this, what we are doing is we have to update our weights. Right? What is updation of weights mean? Change the price. Change the price such that both the predicted values are close to ground truth. Right? It is not one prediction. We are doing two predictions, right? For two scenarios. Both the predictions have to be close to their ground truth. So how will you update it? When we did this, you randomly change the weights. But in mathematics or in machine learning, we have some standard algorithms. One of the most popular algorithms to update weights is an optimization algorithm, which is using gradient descent technique. So some of you might have got, like, at least heard this word gradient descent. Some of you might not have. If you really want to, the one that I can say closest to gradient descent that you all should be aware is Newton-Raphson algorithm. Anybody is not familiar with Newton-Raphson yet? Maybe you guys are familiar? All of you otherwise should be knowing Newton-Raphson algorithm. Newton-Raphson algorithm is kind of a gradient descent algorithm, okay, that tries to find the roots in a load flow problem. So imagine there is a mathematical algorithm which is gradient descent based. It need not be exactly gradient descent. It can be a variant of gradient descent that will help you update the weights. And typically in neural network, we will use what we call as back propagation to update the weights. So this is the most important part of any ANN. So the feed forward pass is reasonably straightforward. You are just solving simple weighted summation plus nonlinear activations and doing it over multiple layers, getting a prediction. That is the easiest part. Then there is a loss function. It can be as simple as difference. It can be a more sophisticated loss function if you have a cross entropy function or something like that. You have equations, so you just have to substitute in it. But once you have obtained the loss function, the goal is to change the weights such that the loss function becomes smaller, or the loss becomes 0 or close to 0, smaller, it reduces. Okay? So we will have a loop going from one loss function. You are going to revise the weights such that the overall loss goes down. So when you do it second time, the entire data set is being passed again with revised weights. Again recalculate loss, check the loss. Okay, so the second time that is done, third time that is done. So each time the entire input data set is taken into a network and a loss function for the entire network has been estimated. We call epoch. Epoch is number, it's like iteration. So epoch means the entire data set has been passed through the neural network and a loss has been estimated. Okay. And then we are updated the weights and so the loop once completing this is one epoch. So you may have to rerun this multiple times to get at weights which will give you closest prediction to actual ground truth. So epoch, anybody know what epoch means in like plain language? Say iteration, yeah, but in terms of plain language, where will you use epoch in English? I'm also not sure, but I'm asking you. Maybe you can check it out in dictionary. It's more like a unit of, like a representation of time, duration in general, but you can, sorry? Subdivision of time, right? So in general, it's a duration of time. Have you heard this Sanskrit word yugam, yuga? Okay. So what is yuga? Yuga, or period of time, right? It's something. So I mean, loosely something like that in general language. But here in artificial neural network, epoch is a count. So it's like when complete data set, not batch, but the entire input feature vector has passed through the neural network and you have estimated the loss function, you have completed one epoch. You have to do it multiple times. So you will have multiple epochs. And if I plot the loss function j over epoch, I should get a decreasing loss function. This is for my training data set. So how do we update weights is using back propagation. So back propagation is one way of like saying like gradient descent kind of an algorithm. But here what we will do is we will find gradients. So the idea is to find partial derivative of loss function over all the weights. But we can use chain rule. So dou j over dou w is dou j over dou y1 into dou y1 over dou w. Okay, something like this. So this is what we will do. So if you look at this network, so rather than directly getting this weight change, we will just do one level backward. And then we will write another one level backward. So each one is called as a local gradient. So we will solve for local gradients, one backward level, and then we will apply chain rule to find the overall variation of the loss function with respect to weights. Okay? So if I had multiple layers, not just an input and output layer, but one input layer, one hidden layer, another output layer. So your loss dou j over dou w would be dou j over dou output layer first, then dou output to first hidden, like second hidden layer from, and then second hidden layer to first hidden layer, then first hidden layer to input layer. So you will have multiple partial derivatives applied in chain rule, and you will estimate the local gradients independently, and then you will substitute into the chain rule to get the overall change of loss function for change of weights. Okay? This is the crux of ANN. If you can understand and implement back propagation, you have solved ANN. Because everything else is very clear to you, right? You are just trying to, you want to find out how to update this. Right? Am I clear in what the problem you are facing right now? Any questions at this point? Finding how the weights must be changed. It's not finding the proper weights. It's how weights must be changed so that the loss function minimizes. So it's the rate of change of loss function with respect to weights. So yeah. Exactly. So different optimization algorithms can be used to optimize the weights, as each of you chose different values, right? So that is how you would end up doing it. Yes, please. So you will have to change all the weights of the network. So if you take a neural network, how many weights are there? 1, W1, 1, W1, 2, W2, 1, W2, 2, W3, 1, and 3 comma 2. So there are 3 and 2 entities. That means there are 6 weights here, and then in this there is 1, 2 weights here, and then there are 2 neurons, so there will be 2 biases, right? So 6 plus 2 plus 2 bias. So these are the total number of parameters you will be updating in every epoch. Okay? So that is for such a simple neural network. Okay? Is that clear? Did that answer your question? No, bias is something usually you will do it in the linear function. So when you are trying to do a linear fit, so what is a, so if you really think about this, it has 2 components. There is a linear part and then non-linearity, right? So the linear part is a straight line fit. So straight line has the equation y is equal to mx plus a constant c. That is the bias. So m is the weights, w, x is the input, c is the bias. Initially, you will use all the bias to be 0, and then as you update the algorithm, bias might change from 0. Okay? Okay, so all I'm trying to say is, if you want to implement ANN, there are many tools to do it, but if you want to understand and implement ANN, the most important algorithm you need to learn to implement is back propagation. Okay? And for back propagation, actually I identified a YouTube video that would have helped you learn, but I just realized that I don't have internet connected to my laptop now, so maybe I will have to arrange that. But in the meantime, what I have come up with is I have identified a web page for you to quickly read through. In fact, I would encourage you to take 15 minutes, read through this page, try to assimilate it. This is a page that you can keep for future. Okay, this has given some worked out examples as well, so it's a good resource. It is so log on to this page and try to read through it. You have 15 minutes time. I'll be walking around. If you have any questions, I'll be happy to answer. Okay, but the idea is the activity that you did is essentially a neural network kind of a problem that you would be solving. By the way, this web page is also a good resource for you to bookmark, and if you are planning to use, continue to work on machine learning, they have some good content, like introductory concept level content.
There will be some error. They will make the error.
All of this pure black population algorithm, this course is basically the course grade depends upon black population algorithm only. Now what we will learn. That's the whole idea. It's not difficult, it's just that implementation.
So how are we doing on time? Everybody is able to go through the entire page, especially the example. Maybe 1 more minute. One more minute and then we will start discussion.
So let us come back to the presentation in success.
Okay, and I strongly encourage you to read through and maybe refer to more resources to understand that. It's not a difficult concept, but just application of that in an actual problem can be a little bit intimidating, especially initially. Okay? The reason why I am not going to go deeper into that in terms of mathematics is because you will see that we will be using tools like MATLAB, where all these things are already developed, toolboxes are already available. Okay, so it will facilitate for such applications where our goal is just to classify whether it's healthy or static or dynamic. We have to use appropriate feature vectors, feed it in, use the right parameters, and then we don't have to really be bothered about how to implement backpropagation. Okay? And that is also the reason why I am not bothered into the details of the mathematics in this workshop. But really, if you are planning to use ANN, you must learn about backpropagation algorithm and its implementation. Sorry? ANN with more than one hidden layer is called as deep learning, deep neural network. Okay, so if your ANN has more than one hidden layer, then it's a deep neural network. Anyways, so now that we have some basic understanding of how an artificial neural network works, so you take input data set, you pass it. So let me just redraw that. So you have input, you have hidden layers, input layer, hidden layer, and then you have output layer. Okay, so you take input, you basically have, this is a fully connected network, so you know there are weights here, there are weights here, there are weights here, there are biases here, right? So you will know all those things, right? And then you have predictions, and then you can calculate loss, you update loss, you update weights to minimize loss. So this is the whole process. Now there are certain things that you need to understand. If you let the loss function epoch for a training data set, if you continue to run this training for again and again and again and again, over and over, you will see that the loss function will start to decrease and go down very close. Okay? But what might end up happening in this process is your system is kind of memorizing the outputs for the particular training data set only. When loss function goes low for training data set, that does not always mean you have got a good training model. What you must do is you must validate that trained ANN model. So say for example, at this epoch you have a certain weights. At this epoch you have completely different set of weights, right? So you can take the model here, give it into give a test data point or a validation data and check its behavior. Okay, so usually in ANN, in addition to the loss function for training data set, we will also try to see the loss function for validation data set. So the validation data set is not used in training, right? So it's like a equivalent to a test point, except that it is called validation set because you know the ground truth. So you can actually assess the performance. In test point is something that's deployed in the field and you have no idea about the ground truth. So that is why validation test is what is widely used. Whereas this one, the red color line, is corresponding to training set. So if you have 1 lakh data points, 80% of it will be used for training, 20% will be used as a validation set. And when you do, so using a training, you will extract the weights, that is the model. And then for that model, if you give an input from the validation set, you may see that as you have trained more and more and more, the validation set's loss function would not necessarily go down continuously. You may reach a point where the validation's loss starts to increase beyond certain epoch. What this indicates is the model has started to become overfitted. The model is overfitted. Overfitting of a curve means in a simple straight line, two-dimensional plane, if you have data points and if you are trying to plot a line that matches that is the best fit for these data points, right? Typically what you would do, you will expect a line something like this. This is what you would expect, right? A best line fit for these data points. But a overfit would be something like this. So for every training data set, the loss is close to 0. It is trained with like too many times that you have. So it's like we are all like that. So if you are doing muscle memory, right? We call it muscle memory sometimes. So if you are repeating an action over several years, driving along a certain route, you will, even if your eyes closed, you know where the road has a pothole, where you have a signal with a traffic police. Everything is known to you, right? You will stop somewhere, you will not stop somewhere. That is just overfitted model, right? So in ANN, we should avoid overfitting, or in any machine learning model, we should avoid overfitting, right? So for that, it is important to not only plot the loss function with epoch for training data set, but you should also plot the loss function with epochs for validation data set. And this is a plot which will be asked by all the research communities or industry people whenever you are saying you are working in ANN. They will say, okay, show me this plot. If you do not generate this plot, then nobody is certain how good is your model. Whether it's an overfitted model or a properly fitted model is not known, right? So this plot is very important. So the loss function with the epoch for training set and validation set has to be done, and you can say, okay, that is right. The reason why overfitting happens is the weights have started becoming too large. Certain weights, okay? So to avoid overfitting, what people do is we use what is known as regularization. I mean, regularization is a very much electrical engineering term, right? Regulation, not regulation. It is like regulatory bodies. So if you have electrical engineering, if you are producing electricity, you want to feed it to the grid. There are certain regulatory bodies that say what should be the power quality, right? So like that regularization means we are trying to regularize the way weights can be changed, weights can be modified. So what we do is we try to add to the cost function, or cost function is the loss function. So let me say loss function, which is also the cost function, plus a regularization parameter called alpha times a regularization equation. Okay, so regularization equation. So what is regularization? Regularization, there are different types too. So what we are trying to do is we are trying to make sure that the weights of our parameters or entities in the system do not go to a high enough value that the system becomes overfitted. So we try to introduce a regularization parameter, and usually this is a mathematical function that's function of weights. So we can have just W1 plus W2 up to Wm, like however many weights are there in the system. So such a function is called as L1 regularization. And the objective of L1 regularization is to make the weights 0, because this is a loss function and you want to minimize this, right? The goal of the problem is to minimize this entire loss function. So to minimize this, the weights have to go to 0. If a weight goes to 0 in a neural network, if I have 3 neurons, if the weights associated with the input is 0, then this neuron is no longer existing in my network, right? So with L1 regularization, I may create sparsity in my neural network. That means some neurons will no longer be actively involved in predicting. Okay? So typically L1 regularization is not preferred. What is preferred is L2 regularization, where we will do sum of squares of all the weights. Okay? When we do sum of squares, the weights can never be 0, or this function can never be 0, but it will be a very low value. So we will always end up having a low value for weights when we add regularization equation in the loss function or in the objective function. And this alpha parameter is the weight that we give for regularization. If you make it too high, then, so it's basically, you have two parts in this equation. Which part should be weighted more? This is our loss function, so this should be weighted more, this should be weighted less typically, right? So this is just a regularization. If your regulatory boundary is too strict, then no independent power producers may come to operation, right? So there must be a good way to regularize, right? I hope this is making sense. So this is how we will try to avoid overfitting. In recent, I should not say recent, another popular technique which is being currently used widely is what we call as data augmentation. Data augmentation, from an image processing, it is very useful. For us, we will stick to L2 regularization. Okay, we will not go into data augmentation at this stage. Okay. One more thing that I want to mention, but I forgot, was how will, yeah, you have a question? Underfitting, you have to train more. So it could be because of lack of data, or not enough training has been done. So usually if you run only for this point, the model might be underfit. It's not a good fit yet. So you can run it further and reduce the loss. Okay. So one thing that I missed to tell is, when we have a neural network, when we are trying to get back the weights, like weight updation, we can optimize that process of updating the parameters in using many optimization techniques. So there can be different types of optimization algorithms that can be used. And in each of that, the rate by which the optimization algorithm has to work is called as the learning rate associated with the weight updation process. Okay, so these are terminologies. I am saying learning rate for optimization algorithms that are used for updating weights of the weights. So this learning rate has to be usually small enough that you are not oscillating. I mean, these are again classical terminologies from optimization parlance. If you have not done a course on optimization, it may be difficult. But the idea is, whenever you are trying to use gradient descent problem, if you have a parabolic structure and this is your root, if you start with an initial assumption here, if you have a high learning rate, you may end up going here. And then you will go like this, you will oscillate. So what you prefer to do is, you keep the learning rate small enough that you go here, 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 like that. Slowly you descend. Okay, that is the idea. Okay, so this is another terminology. The last thing I want to talk about is, so when we are talking about ANN, there are so many parameters that the algorithm needs. So there are so many hyperparameters. What are hyperparameters in KNN algorithm? The K value, then how many neighbors we need to tell the algorithm, right? Then only it will use it. So in ANN, there are so many such parameters that we need to supply to the algorithm to work. For example, if you are using input is segregated into batches, how many batches is something you have to put in. Okay? And then the number of neurons, the number of hidden layers. So layer size, number of hidden layers, they are also hyperparameters. The optimization algorithm that you need to do, the learning rate in the optimization algorithm is an hyperparameter. In regularization, what is the weight associated with the regularization? The alpha value is an optimization parameter. And more importantly, how would you start with the initial weights? Initialization of weights in ANN is always done using a random distribution. You will never start with equal values. And that is also has to be done using special random functions. So you have to specify how to initialize weights and biases. So there are so many parameters that you have to feed into ANN model even for it to work well. And the whole purpose of this 1.5 hours of I speaking is to tell you this statement. Okay, so when you go into a tool like MATLAB, and if you want to do eccentricity fault diagnosis, you have the experimental setup done, you collected data, all those things are good. But after that, if you want to implement it for fault classification using ANN, and you have access to MATLAB, how would you do it? So let's say you have raw data, 50 seconds of line currents and rotor field current of a salient pole synchronous machine, which is DC excited. We are using sampling frequency, we have fault conditions, load conditions. So all this data we have collected, we may have to do some data processing. Say for example, I have to take periods, estimate, extract features, right? So first I have taken the unnormalized phase A current, I have normalized it or rescaled it between +1 and -1. I have considered 6 cycles. Then I have extracted certain features like mean, RMS, standard deviation, skewness, kurtosis. These are all time domain features. I have also done frequency spectrum of my currents. I extracted the magnitude of sideband components. So they are frequency domain features. Then I created data sets. Data sets can be comprised of only time domain features of stator current only. That can be one data set. Or I can have a data set where I have time domain features of both stator current and rotor current. Or I can have hybrid features of stator current. Or I can have hybrid features of stator current plus time domain features of rotor current. So my training data set can have different combinations possible. So these are the features. I can extract these features for stator current, rotor current, time domain, frequency domain. So there can be so many features, right? So once I have the training data set, then I will have to enter hyperparameters. Say for example, I use the loss function to be binary cross entropy. It's not a mean absolute error. It's not y minus y hat. It's a different equation. Okay? And then I'm using limited memory, Broyden, Fletcher, Goldfer, Shano. I mean, this is the first time I'm reading out the name. BFGS algorithm for optimization. So there are many such algorithms you can try. Okay? And then number of layers, I can use 1 or 2. Number of neurons, I can choose 20, 30. See, these are parameters, right? You are entering. You will be doing some trial and error initially to understand how this works. Activation functions in the layers. What kind of nonlinear activations can you use? Sigmoid or ReLU or TAN-H, whichever one you want. Layer weight initializer, initial values of W's and biases. So you have 2 or 3 functions in MATLAB, you can choose one. Bias initializer is typically 0 always in most of the cases. And then the regularization weight. lambda is alpha in the equation I wrote is lambda here. So it's 0 or very small value. If it is 0, then that means there is no regularization. So you are allowing the system to go into overfitting mode. Okay. So this is how you will enter data in MATLAB environment, and there is a standard ANN toolbox or ANN function already created for you. So you will just use it. You will call that function or you will use the toolbox. So that is why I did not go into the mathematics of backpropagation, because I'm not bothered as in this research, I'm not bothered about that part. I'm bothered to know what I need to set in as hyperparameters. Okay. So when I do that, this is my classification accuracy for healthy and faulty. So whenever I get, the system is able to accurately 90%, 95%, 97% like that. So what does this mean? If given a new test data point, my ANN model can predict with a confidence of 95% or accuracy of 97%. So 97 times out of 100 it will predict accurately. So you know decision review system in cricket? DRS. That has some accuracy. So it is slightly greater than human umpiring. Okay, so that is the idea. So these are prediction algorithms. The last thing I will say before I leave you, we will go into popcorn after that, is in ANN, the general way to represent results is not just using classification accuracies, but using what is appropriately called as confusion matrices. Okay? They are called confusion matrices because they confuse us when we see it first. But it is a very simple idea. You have the ground truth along y-axis or one side. So this is y, and this is predicted. If you have 1,000 or 100 data points, okay, your predicted matches the ground truth 90 times. And for 10 times, the predicted does not match the ground truth. Okay, so that is the idea. So this confusion matrix is typically used for understanding how many true predictions, how many false positives, how many false negatives are there. So true positive, false positive, true negative, false negative. All those 4 things can be captured in a binary classification system. So typically you will have, I will draw a sample confusion matrix for you. So let us say this is healthy, this is faulty. This is the actual ground truth. And here I have my prediction of healthy and faulty. X-axis is the prediction. So if I am throwing 100 data points of healthy data, only 90 times my prediction gets it. 10 times it says it is faulty. So that means 90 times true positive, 10 times true negative. On the other hand, when I throw 100 faulty data into my model, 80 times it gets it right. But 20 times it predicts it as healthy. Okay? So from this matrix, what we can say is 20 times I will ignore my fault. 10 times I would have stopped my motor and checked even though there was no fault. So both are not good for us. Right? So this is how you look at confusion matrices. So the diagonal, so ideally in a confusion matrix, you don't want any element in the off diagonal parts. You want everything to be in the diagonal parts only. So this is the parts that we are interested in. If we can only enter in diagonal elements, then we can be certain that there is no confusion. It's called confusion matrix because, again, once again, ANN is modeled after biological systems, so us thinking. So we are not 100% confident of our prediction. We are confused to some extent. So how much is the degree of confusion we have? Likewise, what is the degree of confusion this model has? So that is why it's called as confusion matrix, not because it confuses us as readers, okay? So the confusion matrix for my implementation is shown here. So the 91.7% of time it could predict dynamic eccentricity correctly. 93.5 times it could predict static eccentricity correctly. For healthy, it was able to predict 100% of times. Probably it was already overfitted by then. Okay. Usually when you get 100% classification accuracy, you can more or less be certain that you have an overfitted model. What is the tolerance level for this percentage? So it depends on your customer. So if you are selling an ANN model for a cancer detection problem, even if somebody is diagnosed cancerous when they are not diagnosed, when they are not having cancer, that is still tolerated. But if somebody who actually has a tumor which is cancerous, and if you misdiagnose it, that cannot be tolerated, right? So it depends on which quadrant. So some kind of tolerance is in falsely predicting. In worst case, the patient might undergo another test and a doctor might have to see, right? But if you miss predicting it, then that's a bigger problem. So tolerance need not be uniform. It can be. So it depends on the application. At the end of the day, it depends on the customer that is wanting to buy the product. Not yet. But typically we have very high accuracies expectations. So 95% and above would be the typical expectation. Yeah, it is a good model, reasonably good model. Okay. So I hope I have given you some introduction to ANN. I cannot say that I have made you learn about ANN. It's a deep, it's a deep learning that you all have to do. But anyway, so this is a good introduction in my opinion. We have 10 minutes for popcorn, so don't be in a rush to leave. I did go through all your questions, and what I really found it interesting was when I did the derivation, my intention was to show you that it is difficult. And I realized that based on the questions I have succeeded in my motivation. All of you are scared of that derivation now. Most of the question talks about derivation part of MMF permeance analysis, right? That is probably because you are seeing it for the first time, and it was all Greek and Roman, literally. We had used phi and theta everywhere, right? So. So the feedback is we have to change our way of teaching. So that is the idea, right? Anyway, so that is the major feedback I got in terms of questions. Like many of you are scared of derivation. The consoling answer I can give you is, for the nature of applications we are interested in, you don't have to be bothered. All that hard work has been already done by researchers. What you need to be aware is what harmonics you need to expect and what harmonics you need to use for fault diagnosis. Another question I had was about implementing yesterday's assignment, KNN and PCA. I think KNN is fairly straightforward. Probably the way I gave you the data set might have put you off, but had I extracted the features and had I given you one step, like if I had given you check marks, like this is what you need to do first, this is what you need to do next, etc. If I had given you the algorithm, implementation of KNN would have been far simpler. So I think this is a learning for me, like when I do a workshop on such a short scale, I mean short duration, I should yeah, so I think it's I take that feedback very constructively, in the sense that implementation requires a little bit more hand holding than just throwing you at the deep end, go learn. That's not how it is going to work for a short duration course like this. Okay, and then there was a question, probably I did not understand. Machine learning is applied for RMS value of current wave, but why not for kurtosis? I'm not too sure what that means, but you can apply any feature, you can use it as, for machine learning, so that's not a problem. And then the last thing was about principal component analysis. Yesterday we did not have time for applying PCA. PCA, maybe I will try to show you an application before the end of the course using an actual data set. Okay, at least we can go through the code together. And again, MATLAB, if you are using MATLAB, MATLAB has a default PCA function. It's one line, or it's a toolbox where you have to feed in data. So most of these things, as academicians, I would like you to implement and see. But at the end of the day, there are tools available. Excuse me. So if you are not able to do it first time, don't have to panic. You just have to spend some time, and finally you will be using a tool that is available to you. Okay. So you can learn about the PCA function in MATLAB. That's just a single line of code is what you need to do. Okay. So the most important work in machine learning is preparing training set, preparing your data, setting hyperparameters. Okay, and these are the things that you need to be comfortable with, and then the rest, there are already functions and tools available. Okay. Anyways, thank you so much. So we will be, I think we will be breaking for lunch now. I'm not too sure, so maybe I will let Giridhar sir announce. So regarding feedback, so I will be collecting feedback like this, not necessarily popcorn, but some kind of feedback from you tomorrow as well about ANN. So what I would encourage is you go through the back propagation web page, take some time today to read through it. I will try to share with you a YouTube video link, a few minutes long video link that will also talk a little bit about back propagation. Okay? And that will give you an idea. So tomorrow we will, afternoon we will be meeting, but I think there are different sessions are being planned for this afternoon. So I will also be here, but I may not be the speaker for a change. Okay, thank you so much.